Okay, here is a quick little video on that section 9.11 when we're talking about bond energies and bond enthalpies. And as a practical matter, the approximations made in arriving at the average bond values tend to obscure the small differences between enthalpy changes and energy changes. So we can assume that the bond energies and the bond enthalpies are the same. Alright, so you'll be using that handout that I gave you with the bond energies on them. Alright, you'll be using those to calculate the delta H for the reaction. In this case, we have the delta H of reaction of methane with chlorine and fluorine to give Freon 12. You may have heard of them, the chlorofluorocarbons, CFCs. So eating up the ozone. So we want to try to eliminate those. And they've done a good job in doing that. But now we have to calculate. And remember that the overall equation that you want to keep in mind is that it's the enthalpies of the bonds broken minus the enthalpies of the bonds formed. Alright, so that's easy to confuse because we're used to product minus initial. Alright, so not doing that in this case. So what we are doing is that for all intents and purposes we have our reaction and we're requiring some energy here to break them up into the atoms. And then from the atoms, alright, energy is released. So I'll put an arrow down for required, and energy is released when we make our products. So we want to keep that in mind again, that it requires energy to break the bonds, and you get energy when bonds are formed. So what we'd do is we would look up on our table. So I'm going to take CH4 first. So CH4. Now it's important the number of them that you have. The number of them that you have. So in this case, you take a look at it and we can see that we have 4 hydrogens. 4 moles of hydrogen that is bound to 1 carbon. So we want to look for the carbon-hydrogen bond. We would take 4 moles, alright, then look up the value on your sheet, and you would find that it's 413 kilojoules, and that's per mole. Now, just a note, my values may be a little different from those ones on the sheet that I gave you because this is just simply an approximation when we're calculating bond energies, because a lot of it depends on the environment that you're doing this in. So realize it's an approximation, but it's a pretty darn good one. So that, if we do our math, is 1652 kilojoules for that. Okay, so I rewrote it on another page here. So we have our methane and we figured out that that's 1652 kilojoules. Alright, so now we have 2Cl2. And you can see that I'm taking the reactants, the bonds broken for the reactants. So we have the 2 moles of the Cl. So I'm going to take, that will give me 2 moles, and I will multiply it by what's on the table there that it gives me, and I find out that it's 239 kilojoules per mole, and that gives me 478 kilojoules. Alright, now what's left in my reactants? I have the F2 there, and I have 2 of them, so I have 2F2. So it's the same process here, and I'll get my F, and that will give me then 2 moles, and then I'll use my table to figure out what it is. Again, they may be slightly different because, again, these are simply approximations. All right, but good ones at that, like I said. All right, and we get 308. So now what I do is I add all of them up that I have. So the, let me get a different color here. This 1652, 478, 308 kilojoules. I add that up and I end up with 2438 kilojoules. All right, so that is the reactants, the bonds broken. So now we're going to go on to the bonds formed, and I will do that on another page. Product, bonds, formed. Alright, so I used the same procedure as previous to get my reactants, bonds broken. So in this case I'm taking a look at my products. So I have my CF2, Cl2, I have 2 moles of the CF. I've got to take each of the bonds, and then I have 2 moles of my C to Cl. Alright, I'll calculate these the same way. 2 mole times 485 that I get off of the table, and that's per mole. For the CCl is 2 mole times 339 per mole, and that's kilojoules. This gives me 970 kilojoules. This gives me 678 kilojoules. Alright, I also have HF, and that's 2 moles of HF from my balanced equation there. And that'll give me 2 moles times 565 kilojoules per mole. I get that again off of the table. And 1130 kilojoules. And then lastly I have my HCl that I need to concern myself with. That's 2 moles of, excuse me, that's H and Cl. Alright, 2 moles. Look up the value for the HCl bond, which is 427 kilojoules per mole. And that gives me 854 kilojoules. So now I add them all up again, alright, like I did with the reactants being broken. So add them up, and I get a 3,632 kilojoules. Okay, now we can calculate the delta H. Remember that the delta H is equal, let me go back to white, is equal to the energy required to break bonds minus the energy released when bonds form. So we take the previous numbers that we calculated, which was the energy required to break the bonds was 2,438 kilojoules minus the 3,632. That was the energy released when the bonds formed, and that gives us a value of minus 1194 kilojoules. So you can see that it's a exothermic reaction. The sign value for the enthalpy change is negative. This means that 1,194 kilojoules of energy were released per mole, all right, per mole of CF2Cl2 formed. All right, hopefully this will help you and you find it useful.